Visible universe, why there's more to reality than meets the eye. So what the topic of the talk is these giant invisible galaxies in the distant universe that over the last sort of 20 years or so, astronomers have first of all discovered, they were a complete surprise, that there's this entire population of galaxies living in the very early universe that are completely invisible to our eyes. And so I just want to talk about sort of how that discovery came about and what we are learning about these amazing things. So just to start with, just to set the scene, just to talk what we mean when we say invisible galaxies and the invisible universe. It all comes down to types of light that we can't see. You all probably saw the electromagnetic spectrum hanging on the wall of your physics classroom. This idea that there's the light we can see with our eyes, but then there's all kinds of lights that we can't see with our eyes. Sort of invisible light. And this is a relatively recent invention as far as the human race goes. We've already known about this for a couple of centuries. I think if you go back to Isaac Newton or something, the person who discovered an enormous amount about light, the idea of invisible light would have seemed like a crazy contradiction, right? The idea of light that we couldn't see. The discovery comes down to William Herschel. He's the person we have to thank for discovering this type of invisible light. Herschel's one of the greatest astronomical observers of all time. He hand-built some of the greatest telescopes of all. He's sort of working in the 1750s and 60s and 70s. He hand-built these incredible telescopes and discovered all kinds of things, including planetary nebulae, sort of clouds of gas in space forming stars, and the planet Uranus. He was the person that found it in 1781. But for this talk, I want to talk about his discovery of invisible light. So Herschel was obsessed with sunlight. He spent decades studying sunlight. And he noticed this interesting fact that when he put his hands in different parts of the spectrum, he felt different amounts of heat. And he noticed that sort of down at the blue end of the spectrum, no heat at all. Then as he put his hands sort of towards the red more and more and more, it got hotter and hotter and hotter. There's this sort of increasing amount of temperature towards the red end of the spectrum. And then he had this brainwave, which you see illustrated here, to measure the temperature beyond the red end of the spectrum. And he found this incredible thing. He found this huge rise in temperature beyond the red in this invisible part of the spectrum. So he was the first person to find something invisible within sunlight, right? This is the first clue that there was this sort of whole invisible side to the world. Of course, what he was discovering we now call infrared light, which we take for granted, right? The idea of infrared. We're all walking around with mobile phones which are sending radio waves to satellites, and we have Wi-Fi, and we have all kinds of things, right? So we are very familiar with the idea of invisible light. But this came as a complete surprise. Even William Herschel himself didn't really get to the bottom of it during his lifetime. He went away, he even died thinking that this invisible heat radiation he found and normal light were two separate substances. Like, he didn't think of them as one continuous thing, like light going into the infrared. He thought them as two separate substances, like sort of like gin and tonic being mixed together or something, right? Two fundamentally separate things mixed together. But of course they are not, they are the same thing. Infrared light is just a longer wavelength continuation of the visible spectrum, and we sort of discovered that when we found ultraviolet light on the other end a couple of years later. And then sort of this expands into this idea of the electromagnetic spectrum, which I said we've all sort of seen at school. And I just wanted to give a bit of history of it, because this is one of these things we take for granted. Like the electromagnetic spectrum, this picture where visible light and infrared and microwaves and radio are all part of this continuous tapestry. I think is an amazing result. It's a very hard-won scientific result, right? We didn't just sort of know this just overnight. This took years and years and years of a lot of sort of painful scientific detecting to put this together. And you might have seen the way it's often described as the visible light, like the light we see with our eyes being this small part of the spectrum in the middle. But I think it's often not appreciated how small that part of the spectrum is, like how narrow our window to the universe actually is. So there's a nice metaphor for talking about it. So the light we can see with our eyes, the reddest light we can see, has a wavelength of about 740 nanometers, 740 billionths of a meter. And at the other end of the spectrum, the bluest light we can see has a wavelength of about 380 nanometers, right? So that's our window to the world. And that's about a factor of 2 in wavelength, more or less. So all of the visible light we see is contained within this factor of 2 in wavelength. By a nice analogy, a factor of 2 in wavelength also has meaning when it comes to music as well. So in music, a factor of 2 in wavelength is 1 octave, right? So any of you musicians, if you play a note and you play the same note 1 octave higher, those notes differ by a factor of 2 in wavelength. And so we can sort of make an analogy and say, well, if an octave is a factor of 2 in wavelength, our visible sense can be thought of as sort of 1 visual octave, right? So you can think of us being able to see 1 octave's worth of light. And then, of course, the question is, well, how wide is the whole electromagnetic spectrum? Is it, is it an extra couple of octaves? Is it an extra 5 octaves on either side? And the answer, which I didn't quite believe when I first worked this out, I had to double check, the answer is the entire electromagnetic spectrum is about 65 octaves side to side. And our visible spectrum is just 1 central octave, which is incredible, right? So 65 octaves is about 9 grand pianos in a line. And if you imagine that all of those 9 grand pianos being played at once, and you can only hear music from 1 central octave on 1 piano, like how much of the music would you be missing? Like all of it, right? And that's the same is true when we look at the universe. When we look at the universe in visual like optical light, just with our eyes, as we'll be doing when we go and stargaze afterwards, we'll be looking at the universe with our eyes, we are missing 99% of the universe. I don't want to detract from your stargazing experience, but just, bear in mind that behind the stars you can see, there is, an entire incredible universe. So, for example, this is the Milky Way as seen in visible light. If you go to infrared light, long wavelengths, the Milky Way would look like this. And this is exactly the same galaxy, right? This is still the Milky Way. This is just as real as the familiar galaxy we see. It's just, there's just all kinds of things to the invisible universe. So interestingly, what we see here is this is the dust in the Milky Way. We've gone to such long wavelengths, we can't see any stars at all. This is the glowing dust that surrounds the Milky Way galaxy. The reason we use long wavelengths in particular, this is going to be important in a bit later on, the reason we use long wavelengths in astronomy is because they're really good at seeing through obscuring material. Like firefighters, when they go into burning buildings, they use infrared goggles to see through gas and smoke to see the people trapped inside. So do sort of police scanners, right, if they're looking for people running away, the infrared can often reveal them. If I show you this picture here of some bushes in optical light, it's not very much there. If we switch to long wavelength infrared observations, it becomes kind of clear what's going on. Right? There's someone hiding in the bushes. So this is the general message to remember is that the infrared light, long wavelength light, is really good at seeing through obscuring material to reveal hidden things. And so this brings us on to the topic of invisible galaxies. And these invisible galaxies that we can only see using long wavelengths. Okay, so for anyone not familiar, this is a galaxy. This is the Andromeda Galaxy. It's the closest galaxy to the Milky Way. It's our nearest sort of proper neighbour. It's about 2.5 million light years away, which is pretty far. I think some people might be looking at the Andromeda Galaxy outside. You'll probably have a chance to see this galaxy through binoculars. It won't quite look like this. This is what it looks like through a $1 billion telescope. So it won't look quite as good as this through binoculars. But bear in mind that you're looking at light that's 2.5 million years old. And you can see all kinds of things in here. You can see stars, of course. Galaxies are clouds of gas and dust and stars and dark matter gluing the whole thing together. So this is a very nearby galaxy, but of course we live in a universe full of hundreds of thousands of millions of galaxies. This is one of my favourite photos ever taken. It's called the Hubble Deep Field. It's this beautiful view into the distant universe. Everything in this picture is a galaxy. And this is a patch of sky about a quarter of the size of your pinky fingernail if you hold it at arm's length against the sky. So this infinitesimally small patch of sky, there's about 10,000 galaxies in this picture. So around 20 years ago, astronomers got a new piece of technology which allowed us to take long wavelength photos of the sky for the first time. So like wavelengths really, really deep into the infrared. Just to get a tiny bit technical, there's wavelengths around a millimeter. So these wavelengths are about 1 million times longer than the light we see with our eyes. And one of the first things we wanted to do when we invented these new long wavelength cameras was to see what the distant universe looked like. Can we see some distant galaxies as they look in these really, really long wavelengths, 1 million times longer than the light we see with our eyes? What does the universe look like? And it looked very strange and different. So I'm going to show you a side-by-side comparison now of this same part of the universe, this same patch of sky in the light we see with our eyes and these very, very long wavelengths. So it looks like this. So believe it or not, this is the same picture. On the left we have the picture taken in the light we see with our eyes, these short wavelengths, and on the right we have the 1 million times longer wavelength infrared view of the same image. The reason it's really blobby and ugly is because the resolution of your telescope depends on your wavelength, and having 1 million times longer wavelengths means your resolution is 1 million times worse, which is why all these lovely crisp galaxies have turned into horrible blobs. But once you've got over your horror of the blobs, there's some really, really interesting science hidden here. And so the interesting thing is that there's basically no correlation between what's bright in the optical and what's bright in these very long wavelength infrared images. In other words, the infrared image is telling you that there's some really, really, really bright things putting out loads of infrared lights, right? So really bright, powerful, luminous things that are completely invisible in the optical. If we zoom in here, it probably becomes clear. The brightest thing in the infrared image is here. Right, so there is something stonkingly bright. There is some galaxy that's enormously bright here in this image, and there's just nothing there in the optical. And so what's going on? This is very confusing, right? We turn on these new infrared cameras that are seeing these wavelengths 1 million times longer, and we see a completely different universe. We see new galaxies that we've never seen before. So what are they? Like, what are these new galaxies that we've never seen before? So there are a few different questions that we can ask when we think about discovering these new galaxies. We can ask, first of all, where are they? Like, how far away into the universe are these galaxies? Are they nearby things like Andromeda, like a few million light years away, or are they very distant? We can also ask, what are these galaxies made of? And that leads on to the question, why are they invisible, right? Why are there these very bright galaxies? They're putting out loads of energy, remember, but we can only see them in the infrared. We can't see them at visible wavelengths. So why might that be? So first of all, to answer the question of where they are, astronomers measure very distant things using this unit redshift, which a lot of you might have heard of before. For nearby things, I'm using nearby liberally, like nearby things like the Andromeda Galaxy, which is only a few million light years away, we can just use light years to measure it. So we can happily say something's, a couple of million light years away, or even 10 million light years away. But the numbers get pretty big very quickly, and you feel a bit silly saying something is, so many billion light years away. And luckily, because the universe is expanding, things get redshifted, and so that gives us a way of measuring distance. So the universe is getting bigger and bigger and bigger. And as light travels through that expanding universe, it gets stretched and becomes more red. And the further away something is, the longer light has to travel, the more it gets stretched. And so light gets redder and redder and redder as it travels through the expanding universe. And so we can measure the amount of redness, like how much the light has been stretched from our galaxies, as a way of working out how far the light had to travel. And so when we measure the redshift of these galaxies that we saw in these long infrared wavelengths, we find out that they have a redshift between sort of 2 and about 6 or so. So from about redshift 2 out to redshift 6, which doesn't sound all that much, right? Like redshift of 2. Like, that's a small number. I just told you the Andromeda Galaxy is 2.5 million light years away. But even a very, very small redshift number implies an enormous distance. So for reference, a redshift of 0.1 is about 1 billion light years, which is a very, very long way, right? So a redshift of 2 or a redshift of 6 is an enormous distance, which also means that these galaxies lie a long way back in time, because, of course, in astronomy, the further away you look, you're also looking back in time. I told you the Andromeda Galaxy 2.5 million light years away, we're seeing 2.5 million years back in time. So these things at redshift, 2, 3, 4, 5, 6, which are billions of light years away, are a very long way back in time indeed. So if we sketch out the whole history of the universe, start with the Big Bang, go forward to us here sort of 13 or so billion years later, our Earth formed about 4.5 billion years ago, but this is where our hidden galaxies lie in the universe. We're looking back over about 10, 11, 12 billion years of cosmic history to see these hidden galaxies that popped up in the infrared. But here's the million-dollar question, right? This is very bright suddenly, isn't it? This is the million-dollar question. What are these things made of, and what makes them invisible? Like, why don't we see them with normal telescopes? Why did we only spot these galaxies for the first time, about a couple of decades ago? And the answer kind of slightly lies in this image of the Andromeda Galaxy. So I told you that galaxies are clouds of gas and dust and stars and dark matter holding it together. And it's the dust that's the important thing. So can you see these sort of dark stripes? I should have a sticker around somewhere I can point. So you can see these sort of dark dust lanes inside the Andromeda Galaxy. So this isn't missing stars. These aren't holes in the galaxy. These are lanes and streams of dust inside Andromeda, and the dust is blocking our view of the stars. You can see the same thing a bit better here in our Milky Way. If I show you this image of the Milky Way, the reason our Milky Way has all these kind of cracks in is not because there's cracks in the galaxy, it's because there's dust in the plane of our Milky Way blocking the light. So dust blocks light. And the most dusty parts of any galaxy are the parts that are forming stars. Another object we won't be able to see when we go outside and stargaze later is the nebula in Orion. If you think about Orion's belt, just below Orion's belt there's a nebula, which is a stellar nursery forming loads of stars. This is what it looks like, again from a billion-dollar telescope. I don't want to raise your hopes. But you'll be able to see this for real with your eyes, which counts for something. And so this is a star formation region. It's a stellar nursery that's making new stars. If you can see here, I need my pointy stick again. You can see here, this is this really famous astronomical thing, the pillars of creation, right? If we zoom in, we can see this Hubble Space Telescope view of the pillars of creation. And this often gets called a stellar nursery, right? If you read about the pillars of creation in astronomy magazines or whatever, it will call it a stellar nursery that's making new stars. But it's not very obvious from this picture, right? And the reason you can't see the new stars being made is because we're only looking at visible wavelengths. And stars form in very, very dusty environments, and dust blocks the light. And so the way to see the stars being formed is to go to long wavelengths and see through the dust, remember, like the camera seeing through the trees or the firefighters seeing through the smoke. A long wavelength observation with a telescope will see through the dust and that actually let you see the stars. So this is the same picture side by side taken in long wavelength infrared light. And so you can actually see the stars being born, right? You can see these are the tens of thousands of newborn stars inside this stellar nursery that are blocked from our view when we see in the optical. So yes, it now becomes more obvious why this is a stellar nursery, right? But we can't see the stars because they're behind dust. And I just want to show you pretty pictures. I can do this all day. This is the Lagoon Nebula in our galaxy. This is a picture that was released to celebrate the Hubble Space Telescope's 30th birthday. Again, it's another very actively star-forming region, but because it's so dusty, can't see any of the stars. So all the light is blocked. If we go to the infrared, long wavelength observations, we see exactly the same thing. There are tens of thousands of hidden stars behind the dust. But in our Milky Way galaxy, these very, very dusty regions that are completely obscured are just small patches inside the galaxy, right? So there are these little kind of nebulae dotted here and there inside the Milky Way that are these actively star-forming systems. What I want you to imagine is what happens if you take one of these little very actively star-forming regions and just scale it up to the size of a whole galaxy. So first of all, you would have something extraordinarily, fast at making stars. These little stellar nurseries inside of our Milky Way. If you make one of those the size of an entire galaxy, it's going to be making millions of stars. but also because the whole thing would be very dusty, all of those millions of stars are going to be hidden behind dust, and so they'll be invisible. And so that is what we're seeing here, these long wavelengths. Like, so that's what these blobs are, right? So each blob we see is a galaxy in a very early universe, billions of years in the past, that is like a supercharged factory for stars. And so because it's so dusty, we can't see any of these stars, and that's why they're invisible to like optical wavelengths. But when we go to long wavelengths, we see through the dust, and we can see all of that enormous amount of energy pouring out from these new stars. And so I think it's extraordinary. We've discovered these galaxies. If you were a biologist, just sort of putting on a pair of infrared goggles and seeing an entirely new invisible species would be like the most amazing thing of your career, right? But that's what astronomers have basically done. We've gone to longer wavelengths, and suddenly we've seen these new invisible galaxies that like we'd never thought of before. So this is a drawing of one of these galaxies. I wish our telescopes were this good, but they're not. This is an artist's impression of what we think one of these galaxies would look like. And they really are incredible. We call them dusty star-forming galaxies because astronomers are terrible at naming things and we have no imagination. It's the same sort of school of thought that brings you the great red spot on Jupiter. Right? It's just, so we call these things dusty star-forming galaxies, and they are so fascinating to me because, first of all, they are some of the most extraordinarily star-forming systems in the universe. Right? They are the biggest, the brightest, the most efficient factories for stars in the whole universe. We think somewhere around 50% of all the stars in the universe are born in this sort of dusty, obscured star-forming mode that we can't actually see with our eyes. So these sort of invisible galaxies are responsible for about half of the stars in the entire universe. They're also fascinating as well for a scientist because, they're the biggest, they're the brightest, they're the coolest, but they're also interesting because it's really hard to explain how a galaxy can make stars that fast. We have some theories on often the way that galaxies make stars very quickly as if they're undergoing a merger or a collision or something. When we look at galaxies around us, galaxies crashing together are often making stars very, very rapidly. And so one sort of reasonable explanation would be, well, presumably these galaxies are crashing together. This is a supercomputer simulation of two big galaxies crashing together, and you can produce something that makes loads of stars. So you say, okay, well, maybe these galaxies in the early universe are just, are mergers. They're galaxies crashing together and just becoming these enormous fireworks shows of stars. But the problem is that doesn't really fit with pretty much anything else we know about the universe. We have these very good simulations of how structure and galaxies and clusters of galaxies grow in the universe that come out of supercomputers. This is a lot of what we do in Cambridge, actually. We have a big simulation group. And so this is an enormous box of the universe, right? Each tiny little orange dot is a galaxy. So this is a huge chunk of the universe being simulated inside of a supercomputer. And we get the simulations right because what comes out at the end has to look like the universe around us. And if it doesn't, we tune some knobs right until we get it right. And then when we produce a universe that looks like the real universe, we can then go back and study the simulation and get an idea of how the early universe worked. And all the simulations we have tell us that big galaxies crashing together is really, really rare. Right? Simulations tell us that galaxy collisions are rare. But we see these sub-millimeter galaxies everywhere. Like when we actually look around the sky, we see loads of these things. So, yeah, it's a bit of an unsolved problem at the moment. So I'm not going to give you the answer, I'm afraid, because no one actually knows. We are in the middle of this sort of interesting scientific debate to try and understand these galaxies. We see them. We discovered them sort of 20 years ago. We found these new invisible galaxies we can only see in the infrared. We can't really explain them. One of the reasons we can't explain them is because resolution gets worse and we can only study these things at long wavelengths. They tend to look pretty crummy. So, I told you this is a drawing of one. Until recently, this was the best image we had of one of these galaxies, which makes life pretty hard, right? If I gave you this picture and said, what does this galaxy look like? Is this a spiral galaxy? It's pretty hard to tell. Up until about a year ago, I gave a similar version of this talk about a year ago. I had to finish here. But now, astronomers got a wonderful Christmas present last year, which is an amazing way to view the long wavelength universe, which is the James Webb Space Telescope. So I imagine most people here would have heard of it. James Webb is sort of like Hubble 2.0. It is observing the universe in long wavelengths. It's an infrared version of Hubble. It just kind of goes to show you the power of looking at the universe in these long wavelengths. And it's kind of early days. James Webb has only been sending science data back about 6 months, and we've got 20 years of James Webb to go. But we have some sort of tantalizing early results that are already telling us exciting things. And there are lots of early science programs on James Webb designed to study these dusty star-forming galaxies. I want to show you the results of one of them before we finish. These are the results that came out from this paper by Chen et al. At the end of last year, which used James Webb images of about 4 microns to study some of these galaxies. So the reason 4 microns is special is because that is the wavelength of light that normal stars emit at, if you combine it with redshift, right? So if we're observing 4 micron light here on Earth, when that light set out from the galaxy, it was just regular starlight. So at these wavelengths, we're seeing just kind of normal stars. And up until James Webb, this is the best image we had of a galaxy at 4 microns, which again is pretty crummy, right? I will show you the James Webb image of this same galaxy at this same wavelength. It looks like this, which is incredible, isn't it? Like it suddenly looks like a galaxy for the first time. It doesn't look like a blob. And you can see all kinds of things. You can see spiral arms. You can see a core. You can even see sort of tantalizing hints that there might be little kind of blobs in these spiral arms. If I point to them, so you can see, there's a core. You can see spirals. But you can even see sort of this thing, this thing, this thing, this thing. These might be sort of like this sort of knots of intense star formation going on. And so this is the same thing from the paper. So these are some galaxies taken from James Webb. The sort of the white dotted lines overlaid are like the previous best view we had in the radio, which is just a big ugly blob. And then underneath the images are the actual galaxies. And so you can see they kind of look like galaxies. They have bulges. These are the centers of galaxies. The bulges are formed. They have spiral arms. They even have bars. But the most exciting thing, and this is what this paper is all about. All of these galaxies show signs of kind of interacting with stuff nearby. All of these galaxies show signs of sort of being harassed by something. So take a look at this one, for example. So this one is a galaxy that has a bulge, it has some spiral arms, but it also has this big thing nearby, which is sort of the gravity of this is sort of stirring this up a bit. Same as here. You can see this bulge, you can see some spiral arms, but there's also a bunch of stuff nearby. Same here, which is kind of harassing this galaxy. So maybe this is the clue for how these things form stars so fast. It's not quite galaxies crashing together, but maybe if you have a bunch of sort of smaller galaxies orbiting your main galaxy, maybe they can kind of like stir the gas up and trigger a wave of star formation or something like that. Like I said, it's early days, but it's so wonderful to be able to actually give a talk about these things and show what these things actually look like. Because really, I've been talking about these galaxies for a few years now, and I always just show pictures like this and say, can't wait for James Webb. and now we can actually see these things for real, which is so exciting. And like I said, there are lots of early science programs on James Webb designed to study these dusty star-forming galaxies. They're going to be releasing results over the coming years and decades. And I can't wait to see what we find. I think it's going to be a very exciting time. I'm going to finish there because we've got stargazing to go to. I'll do a couple of questions first, and then we'll start stargazing. Who has a question? Yes?
How do we know that our galaxy isn't, or our planet or solar system isn't inside one of those massive dust things?
Oh, so yeah, how do we know that our own galaxy is not? So we know that we're not inside a dust cloud because kind of dust blocks light 2 ways, right? And we can see out to the universe very easily. If you were inside one of these dusty galaxies, you wouldn't be able to see much of the universe either.
Well, what if it's a massive amount and it's covering a decent chunk of the universe as well?
So we know it's not. So it's a really good question. It's a good thing, but we know it's not because we can look out to the universe in the optical, and we can make entire maps of the universe at long wavelengths. And so if we go to long enough wavelengths, we can actually see the dust glowing itself. And we can make good maps of where all the dust is around the sky and around the universe. And so, yeah, we can tell there's not all that much of it. There's also the fact that dust has to be made in stars, right? And there's just not enough stars to make all that dust in the universe. Let me go to a wider slide so I can see you. Okay. Any more questions? Yes?
What is dust? And talking dust, or are we talking sizes of planets?
No, really good question. So, yeah, so more the size of dust than the size of planets. So when I say dust, I do mean dust. Sorry, I should have explained. So yeah, not quite the same as the household dust you get behind your TV. I think astronomers call it dust. I think it's better to think of it as smoke. It's sort of very, very, very tiny particles of carbon and silicon and all stuff like that. So yeah, so think of kind of smoke. Basically, it's made when stars explode. So like exploding stars kind of release their heavy elements as little particles and molecules, and they end up sort of like smoke filling the universe. We should really call it smoke rather than dust, because dust is confusing. Does that make sense?
Kind of sun?
No, much smaller than sand. So like a particle of smoke. So like you can see a grain of sand, right? Like a particle of smoke is going to be microscopic. So yeah, think much smaller than sand. There is a lot of it, yeah. So so even our Milky Way has about 10 million times the weight of the sun in dust. And our Milky Way is not particularly dusty, right? So dusty galaxies can easily have 100 million stars, weight of dust. Like there is quite a lot of it. Okay, question at the back. Yes, question in the middle. Sorry. Was the question why? Okay, we don't know. So yes, you are right. Every galaxy has a supermassive black hole in the middle, including Andromeda, which you're seeing here, including our own Milky Way. The black hole in the middle of the Milky Way is called Sagittarius A star. It's 4 million times bigger than the Sun. As for why, we honestly don't know. It's what scientists very politely call an open question, which is a scientific way of saying we've got no idea. We're working on it. It's genuinely, there are whole conferences when scientists get together to try and work this out. So here in Cambridge, there's a big research group that's trying to understand it. But yeah, it's a bit of a mystery. Maybe you can grow up and solve it for us. That'd be good. Okay, one. I'm sure you're all keen to start. So tell you what, I'm going to do one more question, and then I'll stay behind and ask the questions, and then you can go and stargaze if you want to. So very last question, yes.
So James Webb is just one telescope.
Mm-hmm.
And there are like thousands of scientists everywhere.
Mm-hmm.
Who decides the difference?
Oh, very good question. So who decides who uses James Webb? So it's a committee of scientists themselves. So really the way it works is you have to kind of apply for time on James Webb, and so once or twice a year you have to write what's called a telescope proposal, which is basically saying, I want to look at this galaxy because it's going to be the coolest observation ever and I will solve science, right? And then you send off your application along with all the other scientists in the world that are applying for time, and then what happens is James Webb will assemble a committee of experts. So sometimes you'll get an email saying, hi, we would like you to serve on the telescope committee, and we're going to send you 100 proposals and you have to rank them. And then, so that's basically how it works. If it's like Hubble or James Webb, it's very fancy, and they fly you to a city and put you up in a hotel for a week, and then you get to have meetings and choose your proposals. If it's a less well-funded telescope, you just have to do it on your own in your living room. But yeah, that's the basic idea. Like they're kind of ranked by the community of experts, and we sort of mutually decide which one wins. It's very very oversubscribed. It's about 10 to 1. So yeah, for every 10 proposals that get submitted, there's only one that gets time. Okay, so I'm going to let you stargaze. Before we stargaze, I'm going to be slightly self-promoting and say if you enjoy this topic of the invisible galaxies, I have written a book about this called The Invisible Universe: Why There's More to Reality Than Meets the Eye. It's written about the same level as this talk, so that I promise there's no maths. I promise there's no scary jargon. If you understood what we're talking about, you will understand that. And I start off with infrared astronomy and then go to gravitational waves and dark matter and dark energy and all the bits of the universe that we can't see. So yes, that is around if you want more of this topic. Wonderful. Okay, so thank you for listening. So I will stay around to answer any more questions if you want them. But my colleague Stephanie outside is going to lead you outside for the stargazing. So thank you. Oh, okay, there you go.